Hi, my name is Floyd Hepburn, and I'm presenting our work on SIGNN, star identification using graph neural networks. This research is in collaboration with my co-authors at Swansea University and the UK Hydrographic Office. The motivation for this research stems from the UKHO's examination of celestial navigation, where existing GPS systems can be vulnerable to spoofing, jamming, or outages, and inertial navigation systems accumulate error over time. With that in mind, celestial navigation, which is entirely offline, presents as a possible alternative or backup in navigation systems. Within celestial navigation, the star detection process is largely solved, but the star identification step, which is crucial to CellNav, has seen continual research and development over the years. Our paper presents a novel star recognition approach by using graph neural networks. Broadly speaking, existing works can be divided into two categories: subgraph isomorphic algorithms, which match observed star configurations, the most widely known being a triplet pattern, against a pre-computed database of such patterns. Star pattern recognition algorithms identify each star via a single feature vector that represents the star's local pattern. Usually these patterns are constructed from the distance and relationships between a star and its neighbors within some pattern radius. More recently, machine learning approaches have seen interest, with the notable comparisons in this paper being a CNN-based spider image approach that uses an image representation of each star, and RPNet, which uses a trained autoencoder to create representations that are then identified by a classifier. One primary drawback of almost all of these algorithms, both machine learning and classical, stem from the initial rules and structure imposed to create the pattern and make it usable in the algorithm. Discretization is one such rule that's overwhelmingly common, but these rules lose subtle geometry and precision that affect the identification step. Our approach represents the celestial sphere as a graph in order to leverage graph neural networks to learn patterns with continuous geometry. The sphere is created using the celestial coordinate system from each star's right ascension and declination. Edges are formed between stars whose pairwise angular distance is below a connection threshold set as 3 degrees. Since absolute visible magnitude is difficult to determine accurately and reliably from an image, we instead create a relative brightness as each node's features, describing its brightness with respect to its direct neighbors. Effectively, we want a structure and pattern radius that captures the rich relationships between stars, but one that is still observable within the sort of limited sensor field of views we might expect. As our GNN has 2 GAT layers, the receptive field becomes 6 degrees, which is in line with the comparative works. The celestial graph approach is sensor agnostic, able to identify all stars in an image from a single derived graph, and robust to positional, false, and drop noise. The network learns which edges, features, and relationships matter the most to each star's identification and which are reliable when considering noisy environments. The initial graph is created from the ESA's Hipparcos catalog. It's filtered to stars with a visible magnitude brighter than 6.0. Now it's integral that our identification is able to handle several types of noise if it's to be useful for navigation, which is even more relevant when considering maritime navigation compared to attitude adjustment in spacecraft, which is more commonly researched because the noise types and severity are greater. Broadly, though, there are 4 types of noise: positional noise, which represents an error in the observed position versus the expected position, which we simulate by applying an angular offset to each star's celestial coordinates; dropped noise, most easily associated with occlusion, such as cloud coverage, simulated by randomly removing nodes; false stars, such as aircraft or satellites, simulated by inserting false nodes with features; and magnitude noise, typically from atmospheric effects, which randomly adjust the brightness of stars. As a quick example, we show how this noise affects stars on the celestial sphere map. Figure A has red ticks showing the direction and intensity of the positional noise. B shows the percentage of stars being removed. C shows a percentage of stars added. And D shows how the magnitudes change within the image. This figure shows the architecture of our SIGNN model. Node features go through a linear transform before being used with the connectivity and edge attributes in the first GAT-conv layer. The output of this first layer now contains information for a target node and its direct one-hop neighborhood. This feature, with the connectivity and edge attributes again, goes through the second layer, expanding the receptive field and information gathering into a 2-hop neighborhood. The output, we then apply softmax to get individual node predictions and confidence scores. Broadly, SIGNN uses a 2-layer GAT network. Each node aggregates from its connected neighbors using learnable attention coefficients. After 2 such layers, a linear classifier is used to create node identities for each star in an input image. This example figure focuses on Sirius. Figure A shows the 2-hop neighborhood of Sirius itself, with red connections being direct neighbors and yellow connections being secondary neighbors. All the information from the connected nodes and edges is used in the representation and identification for Sirius. Figure B shows an example sensor input simulated with Sirius at the central bore site. A sensor image would be converted into this graph representation, and then the star identities for each node predicted. Whilst our training is done on the entire celestial sphere graph at once, creating noisy variations using a parametric data loader, testing, in order to represent the input from practical sensors, creates simulated subgraphs like the 10FOV graph for Sirius in the previous slide. This aligns broadly with the approach of existing work, though notably when we come to discussing results, there's no clear single rule for setup and performance. A lot of results are reported by identifying one centrally placed star or among a small group of centrally placed stars. This is because those patterns are most likely to be complete and reliable. The performance against noise types is evaluated, but the difference in approach, both in the overall algorithms and the evaluation and simulation process, does make fair comparison slightly more challenging. For our testing, we simulated about 800,000 subgraph images and made a total of 28 million star predictions. SIGNN significantly outperforms existing approaches, particularly under dropped noise and positional noise and under high levels of noise. Moreover, SIGNN is capable of predicting all stars in an image at once rather than a single centrally placed image, though for our results we restrict this to all stars within about a 4-degree radius from the center in order to better compare with the existing approaches. One issue, though, with comparing these algorithms was the tendency for existing approaches to report their positional error as a pixel error, say 1 or 2 pixels. This stems from an approach that uses the celestial coordinates with a simulated sensor setup to simulate image pixel coordinates, applying noise in that frame before converting everything back to get and use the angular distances. This whole process is both time-consuming and complex, and it also ties the performance to a specific sensor, since a pixel in one sensor has a very different meaning to another. One major advantage of our graph approach was in keeping everything, the simulating, training, and noise creation, inside the celestial coordinate frame. This means our results are entirely sensor agnostic and much easier for future works to compare against. To create the comparison, though, we had to use what information was available about the simulated data and setup from the respective papers and convert everything into these angular distance values. Though we believe that working in the celestial sphere is a more efficient and easier approach going forward. Finally, we looked at the confidence values from the model and how thresholds can be used to improve the system. In navigation, taking an incorrectly identified star as a guiding star is potentially disastrous. So we show that as each star is output with a confidence, or the probability of belonging to that identity, we can use thresholds to filter out the least confidence predictions. At the highest level, taking only predictions with a 0.999 confidence, we end up discarding about half of our correct results, but we also discard 99.99% of our incorrect results. Given the number of stars in an image, this still leaves more than enough for navigational purposes, but with an almost negligible chance of misidentification. Ultimately, SIGNN achieves superior performance for star identification and noise robustness. Our graph representation better retains geometry and precision, allowing for richer learned representations. In the future, we aim to address the edge of image problem, where the representations deteriorate as they approach the edge of the image from lost information, and examine the use of variable magnitude thresholds, aiming to better represent the varied conditions on Earth. Thank you for listening, and feel free to email me any questions.